Today we're going to talk about differential equations that are really motion problems. We did motion problems back when we were talking about derivatives, and so we should know a few things about motion related to calculus already. Um, Normally, our position function will be s of t, or like we said before, sometimes x of t or y of t, or maybe even h of t. So that's going to represent the position of something, usually a particle, at any given t value, time. And then its derivative, s prime, is the velocity, and the derivative of the velocity, v prime, is the acceleration of the function. So that's this. So we got going on over here. We also definitely talked about speed being the absolute value of velocity. Now, one of the things we may not have discussed during the derivatives unit was a common question on the AP test, which is the speed of something increasing or decreasing? And so we can determine whether the speed, not the velocity, but the speed of a particle, whether it's increasing or decreasing by looking at the signs of the acceleration and the velocity. So speed increases if velocity and acceleration have the same sign. In other words, if velocity and acceleration are both positive, then the speed is increasing. But if velocity and acceleration are both negative, then the speed is still increasing. And think about that, right? If the velocity is positive and the acceleration is positive, it must be speeding up. But also, if the velocity is negative, so if it's moving to the left, let's say, has a negative velocity, but then its acceleration is also negative, that means that is becoming the negative number is getting further to the left faster, right? Acceleration is increasing on it. Right? And so if you were to take the absolute value of what's going on there, those numbers would be getting bigger. Right? And the opposite is true for speed decreasing, right? Speed is decreasing if velocity and acceleration have opposite signs. So if one's positive and the other's negative. So the new thing that we're going to add in here, besides that, is that the integral of a velocity function, a definite integral of a velocity function, is going to give us a displacement. Right? And so keep in mind that what displacement means is it means it's the how much the position has changed from A to B. Right? It doesn't matter if I started with, if at A I was at 0 and I went 1,000,000 meters to the right and then another 1,000,000 meters to the left and then 5 meters to the right, my displacement would be 5 because I'm 5 meters away from where I start. If I start here, go all the way over here and all the way back over here, and come right back to where I started, my displacement is still going to be 0. Whereas my total distance traveled is much more than that. And so the integral on a definite integral of the speed function is going to give us a total distance traveled. It's going to make it like those velocities were always positive values. Speed can never be negative, right? So it's going to just accumulate all these distances, both to the right and the left, as positive values, whereas the displacement is just looking at where'd you start and where'd you end. So we want to make sure we recognize that distinction. So we're not going to do a whole lot of problems today. We're just going to do a few of them. We're going to start with this differential equation. ds dt, or v of t, is equal to t squared minus 8 over t plus 1 squared. So this is giving us the velocity of a particle moving along the x-axis, specifically from t equals 0 to t equals 5. And as we said before, the total displacement should be the area underneath our velocity curve. And we're going to suppose that the initial position of the particle is 9. So that means that at t equals 0, s of t is 9, right? Or s is equal to 9. And the first thing we want to find is the particle's position at t equals 1. So what we're going to do is we're going to take the integral of t squared minus 8 over t plus 1 squared dt, and we're going to find a function that represents s of t. So the integral of t squared is just t cubed over 3. And the integral of -8 over t plus 1 squared, that requires a pretty basic u substitution. So I'm going to kind of just write off to the side. Right? We'd have to let u equal t plus 1, and then du would just be dt. So effectively, what we'd be looking at is -8 over u squared, or -8u to the -2. And if we were to integrate -8u to the -2, we'd go up to a power of -1, and divide by -1. So that'd give us plus 8 over u, where u was t plus 1. But we can't forget the plus c. And then we have to find out what that constant is by using this initial condition, that when t equals 0, s of t is equal to 9. So we're going to say s of 0, s of 0, or s of t, right, is equal to 0 cubed over 3, which is 0, plus 8 over 1 is 8, plus c should be then equal to 9, giving us a constant of 1. So if s of t is equal to t cubed over 3 plus 8 over t plus 1 plus 1, then the particle's position at t equals 1, s of 1, ought to just be 1/3 plus 8 over 2 plus 1, or 1/3 plus 5, which would be 16/3. And now that we have our position function, it makes it really easy to find the particle's position at any other time. Right? We can find s of 5, the position at t equals 5, by just doing 5 cubed over 3 plus 8 over 5 plus 1, 6, therefore thirds, plus 1. So what we're looking at there, well, that's 125 thirds plus 4 thirds plus 3 thirds, or plus 1, which looks like that comes out to be 132 over 3. And 132 over 3 should divide out nicely to give us 44. Now, the final question here is a little bit different. If we want to know how far the particle traveled in the first 5 seconds, that's actually going to be an integral of the speed function, right? The total distance traveled. So we want to integrate from 0 to 5 the absolute value of v of t dt. And it's perfectly acceptable for you to just write v of t on the AP test or on one of my tests, rather than writing t squared minus 8 over t plus 1 squared, because it's already defined up here as v of t. So in order to find that, since we don't have to integrate absolute value, we're just going to go in, and we are going to use our calculator to figure out what that value is. So we're going to hit math, option 9, and we're integrating from 0 to 5 of, and we need an absolute value here. So that's in the math window. And then you're going to go over to the second column, and it's just option 1 there, A, B, S. It'll give you some absolute value signs. And we've got, since we're using the calculator, we're just going to use x. So we've got x squared minus, and we have 8 over x plus 1 squared. Dx. And that should show us that our total distance traveled is 42.5868056, or We can round again to 3 decimals, 42.587. And it doesn't look like we were given any units here in this problem, so we don't need to worry about units. And that's our final answer. For this one, we're going to be given the velocity of a particle. V of t is 2t cubed plus 3t squared. We want to find the position of the particle at t equals 3. If its position at t equals 2 is 1. So when look at s of 2 is equal to 1. So we're going to integrate here to get s of t. Okay, s of t should be the integral of v of t dt, which is, well, the integral of 2t cubed will go up to t to the 4th and then divide by 4. So that'll be 1/2 t to the 4th. And then 3t squared will become t cubed plus some constant. And when t is 2, the position is 1. So s of 2 is 1/2 of 2 to the 4th plus 2 to the 3rd plus some constant needs to equal 1. 2 to the 4th is 16. 16 divided by 2 is just 8, plus another 8, plus our constant is 1, giving us a constant of negative 15. So now we have our actual position function. We now know that s of t is equal to 1/2 t to the 4th plus t cubed minus 15. And if we want to find the position at t equals 3, well, then we just need to plug in 3. 1/2 of 3 to the 4th power. 3 to the 4th power is 81, plus 3 cubed, which is 0.7, minus 15. So what we're looking at here is 81 halves plus 27 minus 15. So really it's 81 halves plus 12. And so that ought to come out to be, that'd be plus 24, so that'd be plus 100, or it'd be 105 over 2. And that'd be our position at t equals 3. This time we're given an acceleration function. So a of t is just sine of t. And we're given that the velocity at t equals pi is 3, and we want to find v of pi over 3. So v of t ought to be the integral of a of t dt. And the integral of sine is negative cosine. So we've got negative cosine t plus some constant. And we know that v of pi, which is negative cosine pi plus some constant, must equal 3. So this will allow us to find that constant. The cosine of pi is -1, so this is negative 1, or 1. 1 plus our constant is 3, so our constant must be 2. So we'll go throw that into our velocity function. V of t is now negative cosine t plus 2. And if we want v of pi over 3, we'll just plug pi over 3 in for t. The negative cosine of pi over 3 plus 2. Cosine of pi over 3 is 1/2, so this is negative 1/2 plus 2, or 3 over 2. And we're just going to look at one more today. In this one, we're looking for the position of a particle at 2. But we're only given the acceleration function. And so we're given a couple of initial conditions, one about the velocity and then another one about the position. So first, in order to find the position, we're going to have to know the velocity. But in order to know the velocity, we're going to have to integrate the acceleration function. So v of t is going to be the integral of a of t dt, which will be the integral of 3t squared is t cubed The integral of t is t squared over 2, and the integral of 1 is t. And then we'll add a constant. And I'm going to call it constant 1. So we're gonna end up with a second constant when we integrate again for our position function. So we know that v of 2, which ought to be 2 cubed or 8, plus 2 squared over 2, so 4 over 2, plus 2, plus that constant, needs to equal 9. So we've got 8 plus 2 is 12. 12 plus our constant is 9, so our constant must be negative 3. So we'll write down here that v of t is equal to t cubed plus t squared over 2 plus t minus 3. So we're moving along in the right direction. Now we need to find the position function. So x of t, our position function, ought to be an integral of v of t dt. And that integral should be t to the 4th over 4 when you integrate t cubed. And integrating t squared over 2 ought to give us t cubed over 6. And then add t to it plus t squared over 2. And then subtracting the 3 gives us minus 3t. And then plus some other constant, we'll call it constant 2 this time. And we know that x of 1, which is, well, if t is 1, all those things are just going to be 1s in there. So 1/4 plus 1/6 plus 1/2 minus 3 plus our constant needs to equal 6. And that one's a little bit of a mess. Looks like our common denominator there is going to need to be 12. So let's see, this is going to be 3/12. This will be 2/12. And this will be 6/12. And I'm going to add that negative 3 over with 6. So that should be 9. 9 in terms of twelfths would be 108/12. So it looks like we've got 108/12 minus 6/12 minus 2/12. That's 100/12 minus another 3 would be 97/12. Lovely little constant there. So we've now got x of t is equal to t to the 4th over 4 plus t to the 3rd over 6 plus t to the 2nd over 2 minus 3t plus 97/12. And we need to find x of 2. So I think we'll go to a new page there for that. We got x of 2. And let's see. We had t to the 4th over 4. So 2 to the 4th is 16. Divided by 4 is 4. So we're going to have 4. And then we had t cubed over 6. So 2 cubed is 8. 8 over 6 should reduce down to 4/3. We may need to get a common denominator here in a minute. We may have to increase that back up to where it was, but we'll leave it as 4/3 for now. We plug in 2 there to t squared over 2. That's 4 over 2, which is just 2. We're going to have a plus 2 and a minus 6 from the minus 3t. So plus 2 minus 6. And then we have that constant left of 97/12. And it's not so bad. It's not as bad as it looked originally. The 4 plus the 2 is 6, minus the 6 is 0. So really all we've got to do is add 97/12 and 4/3. 4/3 is 16/12. So if we add 97/12 and 16/12, looks like that gives us 113/12. And that's going to do it for today. Next time, we're going to start taking a look at a way to sketch solutions to differential equations that we may not be able to solve, or ones we may be able to solve also, using what's called a slope field. So we'll take a look at that next time. But that's it for the motion problems for our differential equation.